In this video, we're going to learn how to plot points for a linear equation in MOER. So let's first read the question. The temperature of an unplugged freezer is 95 degrees Fahrenheit. After plugging it in, the temperature decreases at a constant rate of 15 degrees Fahrenheit per hour for the next 4 hours. Now our variables are defined. Let H equal the number of hours since the freezer is plugged in. And let capital F equal the temperature in degrees Fahrenheit H hours after the freezer is plugged in. Plot the points given in the table below on the graph. So here we're given the context for the linear equation. We aren't given exactly the linear equation, but we're just given a few points. And we want to start by learning how to plot points in what we call the Cartesian plane. So I'm going to scroll down a little bit. Here's our table. So notice this is our horizontal axis, or our axis for the independent variable. It's labeled hours and it corresponds to H, which is measured in hours. And this is our vertical axis, which represents the variable F, and it is labeled in degrees Fahrenheit because this is a temperature. Okay. So our first point is for 0 hours before that. So this is right when we're plugging in the freezer. We have the temperature is 95 degrees. We must be in Arizona in the summer. So notice here where these two lines cross, that's called the origin. Typically we don't label them because this value is 0 for both the horizontal and the vertical axis, and it gets kind of cluttered. So you can just go right to this corner. So when H is 0, F is 95. Okay, so notice that these are incrementing by 10, and halfway between would be 5 in between. So this is 95. Okay. Our next ordered pair is 180. So I'm going to go to 1 hour. So 1 hour later, the freezer is 80 degrees. Next we have 2 hours. The freezer is 65 degrees. At 3 hours, the freezer is 50 degrees. Oops, and they should grab pretty close to the point, but that one I moved a little bit. So there's the 50 degrees. And finally, after 4 hours, it is 35 degrees. Okay, and you can see if we were going to connect these dots, it would make a straight line, and we will do that later. But we just wanted to get an idea of what these points represent in the context of the problem. Now here's our next example. We're going to plot points for an exponential equation. So here we have the number of bacteria in a petri dish is doubling every hour. The experiment begins with an initial amount of 10 bacteria. Let H equal the number of hours since the start of the experiment, and let capital N equal the number of bacteria H hours after the start of the experiment. And again, we're given the table with the H is the number of hours and capital N is the number of bacteria. So let's scroll down so we can see the graph. Now notice, just like in the last problem, we have our horizontal or independent variable is represented by H. That was the time since the start of the experiment. And here we have it labeled in hours. So H is for hours. And here capital N is the number of bacteria. So our first point is after 0 hours, the initial number of bacteria was 10. So I'm going to go to 0 hours and click on 10. Then they said that the number of bacteria were doubling every hour. So at 1 hour, we have 20 bacteria. So here's 1 hour, and there is 20 bacteria. And notice right now it almost looks like it could be linear. But this is where, because if you have any 2 points, there's a line between them. But this is where it's going to get interesting, where we get the exponential shape of the curve. So after 2 hours, it doesn't go up another 10 because it's not linear. The previous amount doubles. So instead of 20, we now have 40. So if I go to 2 and then 40, and you can start to see the curve showing up. And then after 3 hours, I have 80. This is kind of hard to do. I'm going to start at 80 and kind of move over to 3 hours. And finally, after 4 hours, we have 160. So here's 4 hours. 160 is right up here. So I'm going to move to the left till I hit this value. Okay. So notice this is increasing, but it's not increasing like a line. If it was increasing like a line, it would keep going this way. It's increasing more quickly. And you might see that the shape of this curve, it kind of looks like the letter J. If we had another one going up even higher, you could see the J better. And sometimes we call this a J shape for an exponential function.